Good evening. So I wanted to start the video by apologizing to the 1 to 2 people that actually watch my videos for not having a video in a while. I've just been particularly busy. I've actually been trying to go to Cambridge of all places, which those who know me know that's not something I would usually want to do, nor is it something that I'm very likely to do. So I'm not expecting much of a result from this, but that's beside the point. That's just an explanation as to why I haven't really been here. Too busy stressing about that. Secondly, I have a pomegranate again this time, but not a full pomegranate. This one, I didn't particularly have the energy to gut like a fish, so I bought it pre-gutted. Um, Now today I wanted to do something cool, something cool that I came across while thinking for the past couple of days. And for those of you that don't have at least an A-level understanding of maths, I'll define a couple of things before I start. The first of which being a Taylor series. All a Taylor series is an expansion, an infinite expansion of a function in terms of that function's derivatives at a single point A. And a Maclaurin series is just a Taylor series where A is zero. So that all sounds quite complicated. So I'll just write out a general formula for you that most will use to define this. And we can start off by saying that f of A plus f prime of A times x minus A over 1 factorial plus f double prime of A times x minus A squared over 2 factorial plus dot 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 f to the n A x minus A to the n factorial. I mean, that's your kind of description of a Taylor series, right? And now a Taylor series is not an approximation of a function, it is the function. However, if you use just one or two or three terms of a Taylor series, then it's not going to be accurate at all the further you go out. Well, yeah, it's not going to give any value that's correct more than x equals 10 or whatever. So something that I was thinking today, or yesterday actually, I was using Desmos, and I wanted to, write out a formula for this. Your standard summation formula for this. So I wrote it out, n equals 0 to it, or not to infinity, I just did it to 10, of f of n a x minus a to the n over n factorial. However, I run into an issue here. Well, Desmos can't calculate nth derivatives. Um, it can do 1, it can do 2, maybe it can do 3, but it can't do anything beyond that, which made me a bit funny because I really wanted to do this and I don't want to have to write it out all by hand. I mean, I did do that, but I don't want to do that. Oops. So I thought back to when I first learned trigonometry or first fully understood trigonometry. That came a long time after I actually learned it. And I remembered that something like cosine is just sine with pi over 2 added to the angle. Like if you draw it out, for example, you got your sine, cosine is just starts there. You know what I mean? So I don't know if you can see that. So it's just pi over 2 out of phase with sine. So I realized that a formula you can use for the nth derivative of cosine was just cosine, or actually I'll write it out properly. I don't know if you can see this, yeah. F of fn of x should be equal to cosine x plus n pi over 2, right? Because obviously f prime of x, if f of x is cosine, is just minus sine x, and then the second derivative is minus cosine x, and the third is of course sine x, and then the fourth, probably shouldn't be using dashes, you should be using numbers at this point, but I am me after all. And it repeats like this, and all it is adding 1 pi over 2 phase each time. So a formula for the derivative is just that, right? And now if we, you've seen this from here, the phase just starts here instead, and then you've got, I don't even want to draw that because I'm going to draw it so terribly. But if we then do the Maclaurin series of this by drawing it out, by drawing the sum out, we can draw the sum n equals 0 to infinity of cosine 0 plus pi, well, I did pi n over 2, I don't know why, x minus 0 to n factorial. This, when I inputted it into a calculator, gave me back, or it gave me back cosine x, right? And so I knew I was on the right path here. So I kept going, and I took the zeros out, of course. I mean, that's something that you would do anyway. So if I take the, well, actually, I'll leave that as that, actually. If I then write it out again, cos 2 times x to the n over factorial. That's the same thing, right? Just without the zeros. So I realized that cosine n pi over 2, if I write that out, it alternates between 1, 0 and minus 1, right? So when n equals 0, the answer is, well, cosine 0, 1, n equals 1, y equals, well, cosine pi over 2, if we look here, 0, and n equals 2, cosine pi minus 1, y equals minus 1, and it repeats this infinitely, right? But when y equals 0, this is going to output 0, and it's going to times the whole thing by 0, and one of the terms is just going to be 0, right? So if we get rid of the 0 terms, what we're left with here is just the even terms of n, or 2n, so to speak. That's 2, 4, 6, 8, 10, whatever. So I could just remove this entirely, because this is not necessary. I'm always alternating between 1 and minus 1, and the 0 doesn't matter anymore. So if I then write this out again one more time with my terribly drawn signals, I can just get rid of that, have it as minus 1 to the power of n, keep the even terms and get rid of the odd terms. Now we have this, right? This right here is a series expansion of cosine, and we've derived that, reverse engineered it, from the Maclaurin series for cosine, which I think is just ridiculously cool, personally. And it was like an aha moment when I realized that. And you can do the same with anything, with sine, maybe tan as well. Not maybe, definitely. I just don't know if I have the brain power to do that. And you can also do it with something like e to the x, which is very simple again. And the standard way you would derive this is through the e to the ix equals cosine plus I sine x, which is equally as cool, but it's too common. This I didn't see anyone derives cosine or any trigonometry function like that. Maybe because it's too obvious for most people. But I think it's neat. I think it's quite neat. If we do it with e to the x, again using the derivative thing I mentioned, if we go here, this is a Maclaurin series, so it's at maybe you can't see. Oh, maybe the camera's got glare or something. Maybe I can. There, can you see? Yeah, you can see better now. Maybe. Yeah, if I do the e to the x version of it, we get the sum n equals 0 to infinity of the nth derivative of e to the x, which, as you know, the property of e to the x is it's sequential derivatives of all e to the x every derivative. So its nth derivative is just e to the x, and that's at 0. So that's e to the 0 times, again, the thing we mentioned before, x to the n over n factorial, which is just 1 times that, so you can just get rid of that altogether. Move this back to the beginning. And there you have it, it's as easy as that. That's e to the x, and that's cosine x. Do you see what I mean? Reverse engineering these functions is just unbelievably cool to me. Maybe I'm just getting called out of nothing, but I think this is so cool. It's like a computer or finding a cool thing in a video game or something. But I like this a lot, and it's one of the few parts of maths that I actually really like and would be happy to find on an exam. So yeah, maybe this is a boring video for some, but I thought that it was really cool. So yeah, thank you for watching.